Welcome back. In this video, we're going to talk a little bit about critical points and how to apply this idea of a critical point to functions in higher dimensions, and then work through some examples of how to find them. So we'll start with a definition, and it's really actually a definition that's quite similar to what you learned in Calc 1. If we want to find a critical point of a function f of xy, so we're really just any function that has multiple inputs, we say that a point x naught, y naught is a critical point for f of xy if, and recall how in Calc 1, you probably learned that a function f of x has a critical point at x naught if its derivative is equal to 0 there. Well, in this case, the analogous idea here is that the gradient at that spot, x naught, y naught in this case, is equal to the vector 0, 0. Which really is just saying that both of the partial derivatives here are 0. Or we have the other possible condition if we also remember that the derivative could just simply not exist there. So we could say that the gradient doesn't exist at the point x naught, y naught as well. And this can occur either because maybe the partial with respect to x doesn't exist there, or the partial with respect to y may not exist there, or we could possibly have both. So big idea here, this is just all the same notion as what we had from Calc 1. And the importance of critical points can be tied back into the notion of optimization that you talked about in Calc 1. So I'll kind of summarize that here, but we're going to treat the idea of optimization and finding minimums and maximums in more detail in a separate video. But these are related to finding extrema, in that there's this really important theorem called Fermat's theorem that says that if we're going to find an extrema, we basically have to find a critical point first. Or more specifically, if f has a local extremum at a point P, then that point P had to have been a critical point of the function we're working with. And again, we're not going to walk through this whole process here in this video, but just so you can kind of see how this is going to fit into the big picture later on, we will be using the ideas from this video to be able to do optimization later. But having said that, let's go ahead and jump into some examples of just simply finding critical points for a variety of functions. So this example is going to be to find the critical points of f of xy equal to x squared minus 6xy plus 2y cubed. Okay, so to be able to do this, we've said that critical points occur wherever the gradient is equal to 0 or the gradient does not exist. So our goal here is to find x and y values where our gradient is equal to 0, or the gradient does not exist. So how are we going to do this? Well, let's go ahead and start with this idea of the gradient being equal to 0. Well, that means that we have to set our partial derivatives with respect to x and y each equal to 0. And then solve for x and y. And one thing that I want to note before I jump into this process is that a lot of times we're going to wind up having to treat these as a system of equations because we're solving for two unknowns, and we are going to wind up with two equations to do that with. So just keep in the back of your mind that a lot of times you may have to solve a system of equations. Okay, so let's go ahead and get started on this. So this is working toward this idea of figuring out where the gradient's equal to 0. So the partial with respect to x in this case is equal to 2x minus 6y. And our partial with respect to y in this case is equal to negative 6x plus 6y squared. And since we want to figure out what makes these equal to 0, I'm just going to go ahead and set those equal to 0. And work on solving for x and y. I think that the easiest way to approach this is going to be to start by rearranging this formula because we're going to wind up with a really tidy expression of y squared is equal to x, okay? Now, this is as much information as we're going to get out of this particular partial derivative right here. So I can take this piece and plug it into here to solve for y. So coming back over here, I'm going to swap out the x for the y squared, and I'm going to get 2 times y squared minus 6y is equal to 0. Now out of this, I can factor 2y. I'm going to get y minus 3 equals 0, which means that y has to be equal to 0, or y has to be equal to 3. So now I have my information for y. In order to figure out what x has to be, I can take these guys and plug them into the x equals y squared that we get from right there to get my x information back. So when y is equal to 0, I am going to get that x is equal to 0 squared, which is just equal to 0. So I'm going to have the points 0, 0 in this case. When y is equal to 3, I get that x is equal to 3 squared, which is just 9. So then the point that I get from this is going to be 9, 3. So these two values right here, these 2 points right here, are definitely going to be critical values for our function here, because when we plug them in, we do wind up with the gradient being equal to 0. But it is possible that these are not the only critical values because we also have to consider the does not exist case. Okay, so when we look at this, we kind of always want to make sure to make a note of how we thought about this, even if it winds up being a non-issue, which is what's going to happen in this particular situation. Looking at this function here that we've started with, f of x, y is equal to x squared minus 6xy plus 2y cubed, this is a polynomial. And any polynomial, you can take as many derivatives as you want, and the derivative will always exist everywhere. So we're really actually not worried about the does not exist case in this particular instance because we have a polynomial. So we'll make a note of that here, that the does not exist case contributes no critical points. So its derivatives always exist everywhere. So we get no new critical points from this process. So all the critical points that we have for this function then are just the points uh, 0, 0 and 9, 3. And this would be your answer for what the critical points are. Now, it's really common. A lot of problems will ask you to maybe classify them using a couple of different methods. And that's something that we're going to look at in greater detail in a separate video that will be posted at a later time. But right now, we're just focused on this process of finding our critical points, which is what we've done here. Let's do another example. We're going to find the critical points of the function f of x, y is equal to y squared x minus 2x cubed minus y squared. So remember that our goal is to figure out where the gradient is equal to 0 or where the gradient does not exist. Either way. So let's go ahead and start with this one right here. Saying that the gradient doesn't equal to 0 means that we need our partial derivative with respect to x to be equal to 0, and we need the partial derivative of y with respect to x to be equal to 0. We need both of these cases to be true at the same time. So our partial derivative with respect to x is that's going to be y squared minus 6x squared. And then our partial derivative with respect to y is going to be 2yx minus 2y. So I want these to be equal to 0. So I'm going to have y squared minus 6x squared equals 0. And 2yx minus 2y equals 0 here. Once again, I think that perhaps it might be easiest to focus in on this one first. So I'm going to rearrange this a little bit. I'm going to factor a 2y out from both of these here. I'm going to get 2y times x minus 1 is equal to 0. Now, if we look here, this is going to require that y is equal to 0 to make this true. And here, x minus 1, we could also have the possibility that x is equal to positive 1, and that would also make this 0. So, well, we have an x component and a y component. What do we do now? Well, it's going to be really, really tempting to say, okay, let's stick them together in a point. But we absolutely cannot do that. Why not? Well, notice that if we take 0, 1 and plug it into fx at 0, 1, or at 1, 0, this is going to be equal to 0 minus 6, which is just negative 6. That's not equal to 0. So this isn't a critical point, at least not when we put them together. What we want to do is plug each one of these separately into fx to figure out what the other piece has to be to make this sentence, or to make this true. So, so we need to plug y equals 0 into, or maybe more specifically, plug y equal to 0 and x equal 1 into y squared minus 6x squared equals 0 separately. And solve for the corresponding other component. Okay, so something to be really, really careful for if when you solve for one of them and you get two options here, do make sure that it makes sense over here, because if it doesn't, you're going to have to go through this process of having to solve for the other piece separately. So let's dive into that and see what that's going to wind up looking like. Just so we have it here, the partial with respect to x had been equal to y squared minus 6x squared, which meant that we were looking at y squared minus 6x squared equal to 0. When y is equal to 0, what we're going to get is 0 minus 6x squared equals 0? Well, in order for this statement to be true, we're going to require that x be equal to 0. So y equals 0 actually goes more with x equal to 0 as opposed to x equal 1. So 0, 0 is a critical point. All right, so that was for y equals 0. Now we want to consider the case where x was equal to 1. And in this situation, we are going to get y squared minus 6 is equal to 0. This means that y has to be equal to plus or minus, remember that we could take either one, the square root of 6. This is going to give us 2 critical points, and that's going to be 1 positive root 6 and 1 negative root 6. Great. Okay, and that's pretty much all the critical points that we're going to get out of the setting the gradient equal to 0 part. So what about the does not exist case? Well, once again, we are dealing with a polynomial. So the does not exist part really isn't going to give us anything new. So we really don't have to worry about that too much. We're not going to get any new critical points from the does not exist option. So our final answer for this right here, our 3 critical points in this case actually, are going to be 0, 0, 1, root 6, and then 1 negative root 6, just like so. And that's pretty much all there is to that one. All right, let's look at one that looks a little bit different. We're going to find the critical points for f of x, y is equal to e to the y squared over 2 minus y minus x squared. So this whole thing here is inside of that exponential function. So we have to figure out where the gradient is equal to 0 or where the gradient does not exist. Either way. So let's go ahead and start with figuring out where the gradient's equal to 0. This means we have to find partial derivative with respect to x, partial derivative with respect to y, set them equal to 0, solve for x and y. So our partial derivative with respect to x in this case is going to be, I'll take the partial derivative of what's up here with respect to x, because we're going to have to use the chain rule. So it's going to give me negative 2x, and then the whole exponent part stays as is. Just like so. And then if I wanted to take my partial derivative with respect to y, that's going to be equal to, the derivative of this guy up here is going to be y minus 1, and then e to the y squared over 2 minus y minus x squared. Okay, so I'm going to set each of these equal to 0 and solve for x and y. So I have negative 2x e to the y squared over 2 minus y minus x squared equal to 0. Now, an exponential function by itself will never equal 0, okay? I mean, like if it's having something added to it or subtracted from it or something like that, it could wind up being equal to 0, but in this case, the exponential function by itself can never equal 0. The only time that this whole thing can be equal to 0 is when this part that the exponential function is multiplied, it's multiplied by is going to have to be equal to 0. So in order for this whole function to be 0, we need that x be equal to 0. Okay, so in a similar manner, we can look down here. This just gives us information about x, but we also need information about y. So we look here, y minus 1, e to the y squared over 2 minus y minus x squared. That's all equal to 0. Well, once again, we need this piece out front here to be equal to 0 in order for the whole thing to be equal to 0, because the exponential function contributes absolutely nothing to that. So y would have to be equal to 1. All right, so now here's kind of the tricky part, that it's kind of easy to get this idea tangled up with what happened in the last problem. Since these two pieces of information were obtained from separate partial derivatives, and this x being equal to 0 is completely, like this being equal to 0 here has nothing to do with whatever y is equal to. And this here being equal to 0 has nothing to do with whatever x is equal to. Which means that since these came from like separate sources that really aren't super dependent on each other, we actually can now go ahead and combine them. Okay, there's not going to wind up being any sort of conflict between, okay, well, if I plug 0, 1 into this one, am I still going to get 0? Am I going to plug 0, 1 into this one? Am I still going to get 0? The answer in each case is yes. So 0, 1 is our critical point. Okay, so again, since the information x equal to 0 came from entirely from this one function, and y equals 1 came entirely from this other function, we're good to just kind of squish them together there, since there wasn't any sort of mixing and matching going on. Okay, so what about the does not exist case? So another way to think about this whole does not exist thing is to kind of contemplate just really the domain of your partial derivatives that you're looking at here, and ask yourself, okay, is there anything I'm not allowed to plug into the exponential function or out here? Okay, well, obviously we can plug in anything we want into, like, say, x, for example. And the exponential function, it just has a polynomial up here. We can plug anything we want into the polynomial, and it'll produce some number. And we can actually plug anything that we want into an exponential function. So since we kind of have this chain of functions that we're able to plug whatever we want into, there's really not a problem with there being a spot where the derivative doesn't exist. Same idea applies here with the partial with respect to y. So we can plug anything we want into the partial derivatives. So the does not exist case contributes nothing. Okay. So our only critical point then is 0, 1. And that's pretty much all there is to that one. So yeah, this one started out looking like it was going to be kind of messy, but it actually really winds up being quite straightforward, again, because we're only getting one variable at a time from each partial derivative. In our next example, and this is actually going to be our last one for this video, we're going to see an example of what it looks like when there's a spot that the partial derivatives doesn't exist. So this is going to be fxy equals the negative square root x squared plus y squared, and we are going to find the critical points for this. So again, big thing we're shooting for is that the derivative or the gradient of f be equal to 0, or that the gradient of f does not exist. Okay. So I'm going to take the partial with respect to x. And this is going to be equal to negative x over the square root of x squared plus y squared. And the partial with respect to y is going to be equal to negative y over the square root of x squared plus y squared. This just follows from applying the chain rule to this right here. And since this is raised to the 1/2, when you subtract 1 off when you take the derivative, it winds up being in the bottom of the fraction. Okay. So now we're just going to set these equal to 0 and solve for x and y. So if we have negative x over root x squared plus y squared is equal to 0. Well, kind of similar to in the last problem, how the exponential function doesn't really contribute anything to the function being equal to 0. The denominator here really doesn't contribute anything to this being equal to 0 either. So this means that we must have x equal to 0. We get the same idea for the next one. Negative y over x squared plus y squared equals 0. This means that y has to be equal to 0 as well. Now, again, same as in the last problem, because we found since this one only gave us x and this one only gave us y, and there's no real interaction between these two, we know that 0, 0 is a critical point. Okay? So, what about the does not exist case? So one thing that's a little bit tricky about the does not exist case in working with multiple dimensions or multiple input values like this is that it's not enough to just be like, okay, well, I can plug in, like if x is equal to 0, then that's okay because maybe y is not equal to 0. You have to keep in mind of like, are there any values that they can't be equal to at the same time? So in this particular instance, if we were to plug in 0, 0, for example, we're actually going to get into a lot of trouble. So you just want to keep in mind when you're looking for areas where this does not exist, it could be a specific combination of x and y where you wind up running into issues. However, because x and y are both here, there really isn't any other sort of anything else that we could really plug in here that would make the bottom be equal to 0 or make the inside of the square root be negative because they're both squared. So 0, 0 is really the only thing that we have to look out for. And, well, we actually already found 0, 0. If we hadn't already found 0, 0, then this would be a new critical point. But, we already did find 0, 0. So 0, 0 is our only critical point. Okay, so just to kind of recap the general idea behind what's going on here with the critical points. The big thing is just that same as in Calc 1, we want to look for where the both derivatives, or rather the gradient, is going to be equal to 0, or where maybe one of those derivatives or the gradient as a whole does not exist. And then you solve for those values. You just double check to make sure that it does actually hold for both derivatives here, that it does make those be equal to 0. Double check for the does not exist case, and then those are your critical points. And as we did in Calc 1, later on we're going to be talking a little bit about how critical points are useful in finding minimums and maximums for our functions, so please stay tuned for that.